Differentiating trigonometric functions. Now this is quite a long section, and before we get on to what we normally think of as first principles, we have to look at some important limits. So that's what I'm going to do in part 1 here. When doing calculus with trigonometric functions, we will always be working in radians, and I'll explain why as we go through this. Consider the following diagram. So I'm going to start with a circle. Here's a radius, and the length of the radius is r. And we'll say the center is O, and this point on the circumference here is A. And then we're going to have this line here. And T is the point where the tangent here meets this radius extended. This is a right angle, of course, between a radius and a tangent. We're also going to put this line in here so that we have the sector of a circle and a triangle just inside that. And we'll call this point here B. It should be clear from the diagram that the area of the triangle OAB is less than the area of the sector OAB, and note that's because we've got this little bit of area here that's in the sector but not in the triangle, which is less than the area of the triangle OAT. That should be clear, it's around the outside. So if theta is in radians, a half r squared sine theta, now let's think about that, that's the area of a triangle, half AB sine theta, but the two sides are both r, so hence half r squared sine theta, is less than the half r squared theta. That's the area of a sector if we're working in radians, and that's why we said up here about working in radians. And that's less than a half r squared tan theta, which is the area of this big triangle here. Now that's just ordinary right-angled triangle trigonometry. We have this side over here, which is the opposite, and we know that tan theta is equal to the opposite over the adjacent, and here the adjacent is r, so tan theta is equal to the opposite over r. So the opposite is going to be r tan theta, and then it's just a half base times height gives us half r squared tan theta. So AT is r tan theta is obtained by ordinary right-angled triangle trigonometry, as I just explained. So getting rid of a half r squared, which is common throughout, and note half r squared must be positive, so it's okay with an inequality just to cancel it out. Sine theta is less than tan theta. So tan theta we know is sine theta over cos theta. We can divide through by sine theta because we're talking about an acute angle, and we'll be talking about an acute angle throughout this argument. So from here, as theta tends to 0, we know that cos theta tends to 1. The cosine of 0 is 1. So theta over sine theta, note is in the middle of this inequality, is trapped between 1 and something which approaches 1 as theta tends to 0. It follows that when theta tends to 0, that theta over sine theta must tend to 1 because it's trapped in the middle. Or, if we like, sine theta tends to theta as theta tends to 0. You can try this out on your calculator if it's in radian mode. Just keep taking the sine of very small angles and make the angle smaller and smaller, and you'll find that the sine and the angle approach as theta tends to 0. This is really important when we differentiate from first principles. So let's remember these facts down here. So remember this, and of course this works the other way up as well. If it's approaching 1, and if they're tending to each other, then that way up is also 1. So remember, if you remember this, you can remember all of them. But this is really important when we come on to part 2 and we actually work from first principles. Another limit that is really important for this is the limit as theta tends to 0 of 1 minus cos theta over theta. The problem with this one is that as theta tends to 0, both the numerator and the denominator tend to 0. We know that cos theta tends to 1, so the top will tend to 1 take away 1, and of course theta is tending to 0, and that's the denominator. So we need to look further into this. So the limit as theta tends to 0 of 1 minus cos theta over theta. Now there's a trick to this. What we do is multiply top and bottom by 1 plus cos theta. And note on the top, that means that we can make use of the difference of two squares. So it becomes 1 minus cos squared theta on the top, and theta into 1 plus cos theta on the bottom. Note I haven't expanded that. So 1 minus cos squared we know is sine squared. And then what I've done is taken one of the sines and put it over theta and multiplied that by the other sine over 1 plus cos theta. So essentially what we've done here is split the fraction. We know how to multiply fractions together, and if we multiply the tops there we get sine squared theta back. If we multiply the bottoms we get theta times 1 plus cos theta back. So that's going to be the limit as theta tends to 0 of sine theta over theta times the limit as theta tends to 0 of sine theta over 1 plus cos theta. Now, in doing this, I'm actually saying to you that the limit of this product is equal to the product of two limits. And you're going to have to take that with me just telling you that at this stage. We've not proven it, and we're not going to prove it in this class. Now let's consider what we have here. We've already discussed that the limit as theta tends to 0 of sine theta over theta is equal to 1. So this part here is equal to 1. If we consider this limit, the numerator would tend to 0. Sine theta tends to 0 as theta tends to 0. We know the sine of 0 is 0. And cos theta tends to 1. So this limit tends to 0, 0 over 2. So what we have here is 1 times 0, which is 0. Now that we have established these two limits, we can differentiate sin x from first principles.